Now, how exactly do we get savings, right? It's fine to say that yes, the driver now has information that it can use, but how can it actually save power? And there are basically two things that come into play. One of them is called clock gating and the other is power gating, power domains, right? The idea of clock gating is that dynamic power in general in a digital circuit is sort of given by a formula like this. The C is the total capacitance of all the different terminals that are potentially switching inside the circuit. V is the operating voltage, F is the operating frequency, and this activity is some kind of an activity factor, which basically tells you how much of this capacitance is actually switching at a given point in time, or rather an average value of that, right. So as you can see from here, the larger the circuit, the more the capacitance, which means the more the power. The higher the operating voltage, the greater the power. So the good thing here is if I manage to reduce the operating voltage, it looks great. I can actually get a quadratic reduction in power. The problem is reducing the operating voltage means that my circuit will also run slower, right. So I cannot just arbitrarily reduce the operating voltage, I need to be careful with that. But the other thing that is in my control is that I can actually do frequency scaling, right. I can actually reduce the operating frequency of a particular circuit, maybe not, it depends on what my requirements are. But the point is that if I gate the clock, it means that I basically set f equal to 0. How do I do this? Well, I could either go and deactivate whatever PLL is actually driving the clock line to that particular element, or I could use a simple AND gate and disable it, right. So I put the clock through an AND gate, the other input of the AND gate I make it 0, and that's it, there's no clock coming out. If I make it 1, the clock signal directly comes through to the output of the AND gate. So literally that is why the term gating is used. You can in principle use something as simple as an AND gate. In practice it may not be a regular AND gate, it may be something that behaves like an AND gate but is specifically constructed for the purpose of clock gating. And of course, as we can see, the moment f equal to 0, we have 0 dynamic power. Now, why am I saying dynamic power specifically? Because, well, the rest of the circuit is still on, I haven't turned off power. So there is potentially some kind of static leakage power still being consumed, but that's usually much lower than the dynamic power. So clock gating is a very simple and straightforward way to disable the clock to idle modules and thereby save a significant amount of power. Now the interesting thing is the hardware by itself retains state. What does that mean? It means that, remember what happens when the clock is not toggling? It means there are no edges. What that means is all the flip-flops are going to retain their last known state. So the hardware, in other words, retains its state. It's just that it's not being clocked, it's not performing any computation, right. And what we can do is that we can basically have the runtime power management framework set up such that it can automatically gate certain clocks when you are ready to suspend. Okay. Now a power domain is something related but also slightly different. It means that what you have is a group of devices sharing a power rail. The term power rail basically means, the reason why they are called power rails is because you usually have like parallel lines VDD and ground, in between which you have the standard cells, right. So those are called the rails between which the cells are arranged. So when you have different devices, maybe there's a UART, maybe there's a SPI driver, an I2C, Ethernet controller, a whole bunch of other things that are sharing a power rail, right. You could have a scenario where there's one set of devices that are operating on one set of power rails. There might be something which is perhaps operating at a 3.3 volt supply because it needs to communicate with the outside world. I could also decide that within the context of my overall FPGA, I actually divide it up and part of it basically runs with one set of wires and part of it runs with another set of wires, and I can gate them off individually, right. Now what does that mean? It means that I can basically turn off the power to an entire domain, right. Just like I used an AND gate to basically turn off the clock, I could potentially use something similar to say I actually turn off the power. It can't be an AND gate because I don't really want, an AND gate is not really going to have the capacity to deliver the current required, but there are pass transistors that can actually be put directly in the power supply path and can be deactivated and basically put the entire circuit to sleep, meaning that they turn off power, right. Now, in the context of the FPGA, the PL, right, is usually considered one power domain. It is possible in some cases to divide it up into smaller domains and have different control over the power in different parts of it, but in general, one thing that you can do for sure is that the PL domain can be powered off independently of the PS. So, let us say that you want your processor to continue operating at whatever, some kind of a low speed mode such that it is just active, but none of the actual peripherals, let us say filters, FFTs and so on that you have created are active. You can actually turn off power to the entire PL section, which means that the entire FPGA part, the gate array part of things, can be shut down when it is not needed, and the processor can just sort of stay active and reactivate everything if needed. Of course, that was in the context of an FPGA, right? But what you could do is go one step further, and in general any processor, including the ones that you have in your laptop and so on, tend to have the ability to do what is called dynamic voltage and frequency scaling, right. And the idea is simply this: the dynamic power is proportional to V square times F. The leakage power is not related to F, it is not related to the operating frequency, but it is related to the supply voltage. The higher the supply voltage, the more the leakage power, right. So, it turns out that you can scale this in a lot of scenarios, right. One of the things that can be done is, for example, the Zinc processor, it is possible using software itself directly to control the operating frequency of the processors. In most cases, they can run at 667 megahertz. This is on something like the Z board or the PINC Z1 board. The ARM processor there can work at either 667 or 533 or 400 megahertz, and this can be controlled in fact through software, right. Linux in fact provides something called the CPU frequency framework, right, which manages the CPU frequency scaling. It's software that can actually go in there, write certain registers into the hardware and change the operating frequency of the system, right. You can do something similar for the FPGA clocks, because interestingly enough, in the Zinc systems, what happens is that the FPGA fabric usually gets its clock from the PL, or rather from the PS, right, and it is possible using software to control the clock that is being fed into the processor, into the programmable logic, right, which is good news. It means that you can basically control the clock being sent there through software. Now, obviously the trade-off that we have over here is lower frequency in general means lesser performance, right, fewer instructions executed per second, right. It's good from a point of view of power efficiency, meaning that your power consumption has reduced. The problem is it probably takes longer for any particular computation to finish. Now, many processors, not so much in the context of the Zinc, but many other processors also have the capability of changing the voltage, right. So, some minor adjustments can be made in the operating voltage of the processor. In other words, it is actually possible to change that instead of, let us say 1.2 volts, the system will run at 1 volt. Now, obviously for this to work reliably, you should also reduce the frequency, because if I just bring something down from 1.2 volts to 1 volt, I will no longer be able to drive enough current, I will not have enough switching speed to manage whatever, let us say 1 gigahertz rate that I was working at. So, if I bring the voltage down from 1.2 to 1, and if I bring the frequency down from, let us say 1 gigahertz to 600 megahertz, there is a possibility that things continue working properly. If I do not, then potentially the system can become unstable. I start seeing timing errors and the whole thing can go for a toss, right. So, that is possible in certain kinds of systems, not so much in the Zinc, because over there the power domains by themselves are fixed, but what you can do is turn off an entire power domain if you want to save power, right. Now, one thing to keep in mind over here, right, is that we often talk about power efficiency. There is a subtle difference between power efficiency and energy efficiency that we need to keep in mind when we are designing systems, right. Power is actually the instantaneous power that we are interested in, the V into I, right. So, high voltage, large amounts of current, large amounts of power being dissipated, right. And the problem with power consumption is that it actually gets translated into a corresponding heat dissipation, right. So, there is heat that needs to get dissipated somehow, and the biggest problem that happens is that you need good thermal management in such a system, right. Now, let us say that you are building server racks that are going into a data center. This kind of, you probably can tolerate a fair amount of power consumption, but this is your biggest problem, because thermal management is what you are going to struggle with the most. Because once your systems start heating up, you need good active cooling systems, you need air conditioning, all of that in order to make sure that the system can keep running at high power for a long time without getting too hot. Okay. Now, one of the things, as we saw, is I can do frequency scaling, which means that I can bring down the power. That is good. The problem is, if I bring down the frequency, it also means that a given set of instructions that I have will take longer to execute, because it takes that much longer for that many clock cycles to execute. I still need 1 million clock cycles. It is just that each clock cycle is now, let us say, 1.2 nanoseconds instead of 1 nanosecond, right. So, it takes longer for me to execute. Now, from a power point of view, that is good, right, because my maximum power has reduced and therefore the heat that I produce is less. The issue is the energy remains the same, because even though my power came down, the time increased. Okay, so power into time remains the same. So, energy, in other words, is consumed over the entire duration of the computation, and we can have low power, but if we run for a long time, it can potentially mean even more energy, because the other side effect that you can have in like extreme scenarios is that your static power has not changed, right. It was only your dynamic power that came down when you reduce frequency. So, your static power could potentially get to the point where it basically says, okay, now I still have static power and I am going to take twice as long to execute. So, therefore, the savings that you thought that you actually brought down the, or rather that you kept the energy constant, is wrong. I am actually consuming more energy than before, because it is taking me longer to run, and during that time, extra time, static power was still being burnt. Okay. Now, energy directly is related to battery life, which means that if you have a mobile system or a battery operated system in general, lowering the frequency by itself may not always be the best solution. And in fact, in some cases, you might even find that people opt for a scenario where they actually run at a very high frequency, high voltage, well, not high voltage is relative of course, but something a high performance mode, finish the computation extremely quickly, and then go into a deep sleep mode where the entire system is powered down and even static power consumption is reduced. That could potentially give even better savings than just operating at a low power for a long amount of time. Okay. Now, there is one other thing that is possible only in the context of an FPGA, right. It is something called partial reconfiguration. So, the Zinc 7000 and many other FPGAs, right, both from Xilinx and from the others, Altera and other companies, allow you to do what is called partial reconfiguration. You can essentially reconfigure just a part of the FPGA and not the entire thing, right. Now, what is the use case for this? Why would I want to do something of this sort? Remember that the total power being consumed is proportional to C, the total active area, right, the active components that are present inside the circuit. So, if I can basically have different configurations of the FPGA where I load in specialized accelerators only on demand. When I need it, I activate it, and when I do not need it, I basically unload it, and that entire section is not even active. There is no clock going there, there is nothing happening. So, it is not going to consume, well, it is at least going to consume less power. There might be static power, but at least no dynamic at that point, right. I could still use things like clock gating and so on. This is another approach that could be used, right. Now, how do I use something of this sort? I can actually boot up with a minimal FPGA configuration, keep the system active, the operating system comes up, everything is okay. When the camera, for example, becomes active, I load an image processing overlay or a module, right. So, the partial reconfiguration just activates that particular section and says, yes, this can do certain kinds of image processing. Once that is done, I sort of unload it, reconfigure it perhaps for audio processing and proceed in this way, right. Obviously, it comes with drawbacks. Every time that you are loading and unloading, that is taking time. That's also consuming energy, because there is a certain amount of activity in terms of loading the bit stream from an external source, putting it onto the FPGA fabric and so on. So, it is not coming for free, right. This makes sense only if you are going to do this reconfiguration, keep it active for a certain amount of time, then maybe switch over to another one, keep it active and so on, right. Now, the benefits of this could also be that you have smaller bit streams, right. What I mean by that is, you may not have enough capacity on your FPGA to do both image processing and audio at the same time, but you could swap them around, do one then the other and so on, right, and that gives you smaller overall bit streams, potentially the ability to use smaller FPGAs. You can reduce your static power consumption by basically reducing the active area and the dynamic allocation of how much of the FPGA is actually being used. Obviously, it comes with a significant amount of complexity. Floor planning becomes much harder, right, because you have to actually, even though it sounds like I can just swap out part and put something else in, you need to be aware of this right from the time that you are designing your RTL and then doing the floor planning, something that we normally don't think about because we assume the tools will do it for us. If we want to do partial reconfiguration, we need to be very careful about which part of the FPGA is going to be reconfigured and make sure that the parts that we want go into that part of the FPGA, right. So, there are sort of the entire design has to be partial reconfiguration aware, and that makes it a bit more complicated.